Okay, so take like 18 on trying to make a video on substitution reactions. Here's to hoping that I make it all the way through this video without saying something stupid. So in this video, I'm gonna try to help you understand how to figure out what type of reaction is going to take place with a given set of reagents. All right, so let's start with something, I guess, a little simpler, and then we can kind of build off of that maybe later in this video, I don't know, or maybe in another video. So let's start with something pretty simple. So we'll start with something like this, and then given something like that, and yes, this is looking great. What are we going to do? This could absolutely be a test question. And so if you flip the page on your test and you see something like this, after you're done freaking out, how can you correctly assess what is going to happen given these reagents? So let's start this process. The first thing I would do, so first of all, you have to look at all of your reagents, any conditions, and let all of it take part in your considerations. The first thing I would do, I don't know, let's pick a compound. You can start anywhere. There's no one thing that's going to be the make or break on your decision. That's the nice thing about doing these types of things, is everything has to support your decision, not any one thing. But let's start with 1-bromobutane. When I look at 1-bromobutane, the first thing I see is bromine bound to a primary carbon. So I'm going to immediately see that dipole. So the dipole is going to be pointing towards the halogen, okay? And that means that the halogen is going to be a partially negative. So however partially negative the bromine is, well, that's how partially positive the carbon's going to be. Okay, so that's helpful. I would probably recognize that bromine could be a leaving group as Br-. So bromide could be a leaving group, but it can't be via SN1. And that's because, why is that? Because you can't generate a primary carbocation. So this leaves me with, well, could I do SN2? Since it's a primary position, yes, we could do SN2. Okay, so now do I have any other reagents that will help facilitate an SN2 type of reaction? So let's look here, NaSH. So what is this? You know, I could give you a reagent that you've never seen before. How do you correctly assess, first of all, even what it is before you can even determine what it's going to do? So, you know, how do I go through that process? Well, for this type of reagent, I'm seeing Na. Okay, so whenever I see Na and then other letters next to it, I'm immediately thinking, Na and something else. That's going to be a sodium cation. So the example, you know, the analogy for this is sodium chloride. Okay, those are like two peas in a pod. So wherever you have Na and then other stuff, what you have there is a salt, where the sodium is a cation and everything else is going to be the anion. Okay, now what atom specifically is the ion on? Well, I have an S and an H to choose from. Which one of those two atoms will be more stable, holding on to excess electron density? I'm going to go with sulfur. Okay, for a few reasons. You know, but I guess the easy way to go about it is, well, sulfur is under oxygen, okay, so it's kind of in oxygen's group. it's larger than oxygen, so that excess electron density is in a shell further away from the nucleus than oxygen, so the nucleus is even less aware of it being electron rich, so this is going to be more stable, if you will, than an OH minus. So that's how I would assess that reagent. Now I'm seeing formally negative, okay, so there is a formal negative charge on the sulfur. So this is going to be pretty nucleophilic. Now how do I know that? So it's larger than oxygen, just physically, okay? It's the sulfur atom is larger than oxygen. So why is that making it nucleophilic compared to oxygen? Well, compared to oxygen, I guess I'll go ahead and draw this down here and maybe erase it. Let's go ahead and change this back. So if we have an oxygen atom, let's just relatively say its valence shell is that big, okay? Comparatively, if we have a sulfur, it's going to be something like this. So why is this important? Why does this matter? How is this helping me interpret how this is going to behave? Where do I put you? Let's go over here. And then I'll move sulfur over here. So how nucleophilic an atom is, it has to do with the polarizability of that valence shell. And polarizability means how much reach will that atom have to grab a nucleus? Well, how much reach it has is how much volume it has to its valence shell and how much that can be distorted when the electron density of the nucleophile is kind of moving towards the electrophilic position. So if oxygen has, set amount of volume associated with its valence shell, well, just think about how much more volume sulfur will have. Sulfur's reaching off the page over here. So, this distance, this is the reach that atom has to reach out and grab an electrophilic position. We'll just look at how much more reach that sulfur atom has. Well, how much reach it has is how nucleophilic the atom can be. So sulfur has a longer reach, is more nucleophilic than any oxygen variant. Okay, so like this thiolate is going to be more nucleophilic than a hydroxide variant. So let's get rid of all of this now. Delete. Playing with the iPad. Okay. So pretty nucleophilic is, well, let's just say we're being conservative in that description. This is very nucleophilic. Okay. Well, now the last thing we need to discuss is, let's see. Oh, I'm going to choose this color. What is DMSO? What is that? Dimethyl sulfoxide. And it looks like this. Dimethyl sulfoxide is a solvent, and it is a very polar solvent. But if you notice, there are no acidic protons. What do I mean by acidic protons? Protons that could possibly be abstracted as an H+. Not necessarily like acidic in terms of like HCl or H2SO4, anything like that. Just a protic solvent is what I'm trying to say. Protic solvents are solvents that have an abstractable proton. An abstractable proton is, in some way, you would call it acidic. Okay, not necessarily the pKa of the proton has to be in the negatives or anything like that. It just means given possible conditions, it is abstractable. So this is a solvent. It's very polar, no acidic protons. What is that telling me? It is a polar aprotic solvent. Okay, so what is this doing? Solvating everything else. And doing nothing else. Okay. So now let's just redo this. All right, so now that I guess we can go back and kind of, I guess, bring all of this together. So 1-bromobutane, it can't do SN1 chemistry because a primary position cannot generate a carbocation. The only type of chemistry we can do at this position is perhaps SN2 chemistry. But this is telling me, in order to do this, go find a strong nucleophile to allow it. Or I guess I should say to force it. Okay, well, so I'm going to go look somewhere else, and I think I found one. Okay, so I found that right over there. Great. Now the problem is sodium thiolate is a salt, right? Pretty much kind of like sodium hydroxide is a salt or sodium chloride is a salt. Well, what are salts soluble in? Salts are soluble in water, right? You can throw in sodium chloride to your heart's content and it'll just keep on dissolving. So water is a very polar solvent. Salts require very polar solvents to be solvated. So we need to find a solvent that can solvate our salt, polar enough to solvate our salt, but also solvate our organic compound, our 1-bromobutane. But we need to use a solvent that in no way can take part within the reaction. The only thing we want it to be able to do is introduce the other reagents and make sure that it itself doesn't take part in any of the reaction fun that's going to take place. DMSO is one of those solvents, okay? DMSO, DMF, acetone, dichloromethane, these are all solvents that are very polar, okay? Maybe I'll draw them down here. So DMF is dimethyl formamide. So what is that? That looks like this. It's a very polar solvent, and if you notice there are no acidic protons, like proton bound to an oxygen or a nitrogen or something like that, that could be possibly abstracted. Acetone, so acetone looks like this. If you notice, it kind of looks a lot like dimethyl sulfoxide, right? Dimethyl sulfoxide right here, except instead of a sulfur in the middle, it's just a carbon. Okay, and then dichloromethane, DCM, dichloromethane, so there's going to be a C, and then there's going to be 2 chlorines bound to it, and well, how many carbons does how many carbons? How many hydrogens? 2. Dichloromethane. Pretty polar solvent. Okay. I said in the beginning of this video, I'm going to try to minimize the dumb things that I say, so let's move on. Okay. So I've identified my electron poor spot. I've identified my leaving group. I'm sitting here going, man, this could possibly leave. Leave if it was forced to leave. Second order kinetics. Okay, so I will use black mechanism arrow. I guess I should probably erase all this now that I've kind of identified how everything is going to come together. And so now we've got this. And then Br minus. Now remember, we've got this sodium cation that's sitting over here doing nothing, so it's going to coordinate. So we're going to have sodium bromide salt and this thiol product. So that was a 15-minute and 27-second description of a simple SN2 reaction and how to deduce how your reagents are going to behave. Maybe in a subsequent video I'll come up with some reagents that might be a bit more nebulous as to, how clear is it, what's going to happen, and maybe we can spend a little bit more time deciphering. Thanks for listening, guys. Bye.